Okay, good morning, everybody. So in the last class, at the end of the last class, we kind of summarized that there are two kinds of density-based clustering algorithms. One is model dependent or model based, another is model free. In model based, we explicitly model the underlying density using a PDF, a probability density function. And then the different Gaussian components of that PDF correspond to the clusters. That is what we have done with the expectation maximization using Gaussian mixture models, the EM-GMM algorithm. The other possibility in the same approach is to just estimate the density without using an underlying function, and then hide that in the data set will be considered clusters. So I mean, I'm simplifying it, but there's some more details there. So let us look at the second kind of clustering algorithm. Most prominent example of that is Dbscan, which stands for density-based spatial clustering of applications with noise. Okay, so let us see how this works.
Sir, I think you are not audible.
Not audible?
Yeah, in between there was a pause actually. Maybe just.
Meaning my audio is on.
Okay, fine. Now it is fine. Now it's fine. Yeah.
Okay. So we've got up to here, right? Density-based clustering.
Yes.
Yeah. So the thing is, with k-means, you have all these problems. It gives you only globular clusters and doesn't work well if the cluster sizes are very different and densities are very different and all that. And so as you can see in this example, so they have taken a bunch of data sets and then applied k-means clustering with or k-media clustering, which gives similar results for k equal to 4. So you see that in the first case, in the far left, you have one tiny cluster here. I hope you can see my cursor, and then like a large S-shaped cluster, and then another. I don't know what this shape is. Okay, so there is another little wiggle here and another small cluster. So when you do k-means clustering, it has broken them up, left and right, literally, and it hasn't got most of the clusters well. Only the small clusters, which are more compact, kind of globular, it got them, but these huge extended ones, odd-shaped clusters, right? It won't be able to get it. Even here in the second example, these are kind of globular clusters, but they are of different sizes and densities. So again, it broke up the large cluster into multiple clusters and kind of merged a small cluster with one of the larger clusters, and so on. So it made a mess of the whole thing, right? Same thing in third example also is very similar. So k-means clustering is not suitable for certain kinds of data distributions. So this is where Dbscan can give excellent results. Let us see how it works. Okay, so the basic idea of Dbscan is, so you have, let me draw something. So you have a bunch of points. So this is one cluster, and this is another cluster, and maybe some loose data. So here and there. So you see that there are prominently two clusters here. This is one, and this is one, and these are noise. No, you don't want to, include them in any cluster. So how do you do that? You need to figure out that all these points have high density. If you take, let me put more points here to convey the concept. So what happens is, if I look at any point here, look at the local density. So it is high. Okay, and let us assume the density is uniform everywhere. So density here is number of points per unit area, right? And if you go to a point on the edge, right, density typically becomes something like half, because there's the points only on one side, other side there are no points. But so thing is, it's not enough to just label points as points belonging to high density regions. We should also be able to understand and determine that if two points come from nearby high density regions, they belong to the same cluster. Okay, so this is the most important aspect of density based clustering. So first of all, I have determined that a given point is in a high density region. So this is a high density region, whereas this point is in a low density region. Okay, so that's the first thing you need to determine that, and that's not very hard. Once you determine that, if I have 2 points which are nearby and both of them come from, or you have determined that both of them come from high density regions and they are nearby, then both should be in the same cluster. So like that, you can kind of combine points and determine the cluster, then the extent of the cluster, right, by just joining and annexing, right, points which are nearby and belonging to the same high density region. Then the problem comes when you go to the borders of such a region. Because in the borders, the density necessarily will be low, right? Something like half. So, but the border points are still, the points in the near the border are still part of the same cluster. So how do you determine that? So there you say that, okay, fine, right? You yourself may not be in a high density region, but you are close to another high density point. Therefore, you belong to the same cluster. So this is how you determine the entire cluster, and then so like that you give labels, same label to all the points which are nearby and coming from the same high density region. So a good analogy to this, before we start getting into the algorithm and the details of the algorithm, a good analogy to this is how we form friends networks. Right. So let us say you have a friend, and if you have a friend, you and your friend, let us say you can give a name to your friend circle. Every one of you will have a friend circle. Right. All the people belong to friend circle must be given certain label. Let's say circle number 1. Okay, something like that. So you and your immediate friend are in the same circle. That friend has some other friend. You may not be knowing that friend, but so that other friend then will automatically come and join, will be part of the same circle 1. And that other friend will have some other friend. So that person also will join circle 1. This goes on and on until you reach a point where the friends are not great friends, it's just acquaintances. So acquaintances won't be allowed into your friends network. So your network will stop at some point because you cannot include the whole world, because beyond a point your friendship links will be very weak. They'll be just acquaintances. So you'll end up with a network where all the people within that network will have strong friendships among themselves, and they'll have weak friendships with people outside that network. So that will be your friends network. But in this case, obviously, unlike k-means clustering, there's nothing like a medioid or a mean vector. There's no centroid here, right? So it is, the label is simply propagated from node to node or point to point simply by the principle of adjacency. Okay, so that is how you grow the cluster here. So let us look at some the actual steps for constructing this. So here we need to introduce 3 kinds of points. That's how the Dbscan works. The first point is core point. The core point is one which has more than a specified number of points within a radius called epsilon. So there are 2 parameters here. One is a certain threshold number of points, a specified number of points. Okay, that specified number of points is called min points. This is a given parameter. Just like in k-means, k is given. In Dbscan algorithm, this min point must be given. One more parameter that is given is this epsilon, which is like the radius. So basically what you are saying is, if a given point has more than certain number called min points in an epsilon neighborhood, in a neighborhood of radius epsilon, then that point is considered to be in a region which is of high density. The high density is given by this threshold, is specified by this threshold, right? So if that point comes from a high density point, and therefore it is called a core point. So it is like if I have a cluster like this, a point deep inside, right, is a core point, and a point close to the border is a border point. Okay, so the core point is defined like this. If it has more than min points within an epsilon neighborhood, right, then it is a core point. So this is epsilon neighborhood. A border point then is obviously it is in a less is local density is lesser, so therefore it may not have as many as min points within its epsilon neighborhood. But the border points is known, it's in the neighborhood of a core point. It's like your friend circle. Let us say you're part of a rich friend circle, right? You have all the privileges of being in a rich friend circle. So there's one guy. Sorry for giving this kind of analogy, but there's one guy who himself is not very rich, but he has a rich friend. So to the extent he or she gets all the privileges of being in the network of a rich bunch of rich guys. So like that here, a border point is itself not a high density point. That means it may not have as many as min points right in its epsilon neighborhood, but it is close to it is within the epsilon radius of a core point. Therefore, it is a border point. Now there's a third kind of point which is a noise point, which is any point which is neither a core point nor a border point. So a point out there here, like solitary point. Right around that there is nothing. So it doesn't satisfy min, but it cannot even be a border because nearby there is no core point. Okay, so once you have these three kinds of points, you can now go ahead and construct the clusters. So let us see how it is done. So again, this border point, this is a core point, and the outlier is a noise point. So epsilon neighborhood is all the points. So the whole epsilon radius, the sphere of radius epsilon. Okay, and all the points within that sphere. Core objects is epsilon neighborhood of an object which contains at least min points of objects. Let me skip that. Now these concepts give us a new concept called directly density reachable. So that is if an object Q or data point Q is said to be directly density reachable from an object P from an object P, if Q is within the epsilon neighborhood of point P and P is a core point. So P is a core point. Q is a test point which we are considering. What are we trying to determine? Is Q directly density reachable from P? Okay, and when will that happen? If this distance D is so this is Q, the distance D is if D should be less than epsilon, that is one thing, and P must be a core point. If both of them are true, then Q is density reachable. So basically, we have core points and we have those fellows who are very close to the core points because all of them will be part of the same cluster. So that's why you need this concept. Okay, so this is called directly density reachable. So once you define this directly density reachability, right? You can apply that sequentially and have a much more a broader concept called just density reachable, not directly, but just generally density reachable. When do we say that an object P is density reachable from Q with respect to parameters and epsilon and min points? If there is a chain of objects P1, P2, and Pn, with P1 is equal to Q and Pn is equal to P, such that Pi plus 1 is directly density reachable from Pi. Okay, so basically you have a point P. Okay, and so point P and then a point Q is here far off, right? And so you have other points. So I'll call this point P1, P2, and okay, so this is Pi and Pi plus 1 and so on. And finally, you have Q at the end of a whole chain of such points. So P1 is density reachable from P because P is a core point right? And this distance is less than epsilon. Okay, so that is, so you have got up to here, and so then P1 and P will be in the same cluster. Now see if P1 itself is a core point. Again, apply the same condition. Are there uh, more than equal to min points number of points within its epsilon radius? So then P1 is a core point. Okay, then next consider P2. Is P2 within epsilon radius from P1? Okay, then P2 is delta density reachable from P1. Right, again, so similarly apply the same principle again and again. So is Pi reachable from Pi minus 1, then Pi plus 1 reachable from Pi, and so on, finally Q. So it's like, you have a long kind of a lake, you have a big lake and a river or a wide river to cross. This is one bank of the river, this is the other bank of the river. Are there some kind of rocks in between so that you can, which are not very far from each other? Right, neighboring rocks should not be very far from each other. So you can jump from one rock to another and reach the end of that whole series of rocks and cross the river. So that's a kind of a concept that we are looking at here. So by this principle, you can go from P to Q, and this is called reachability. Just an example. So I take this point, that's a core point. Okay, so then all the points within its region will also be put in the same cluster and so on. I'll give you a better example which comes later on. So the way it works is first eliminate all the noise points. What are noise points? The number of min points is number of points is less than min points, and it's also not very close to any core point. Okay, so remove them. So first you have to label all the points, the core points, border points, and min points. Okay, then the next step is label the clusters. Now, how do you do that? First, remove the noise point. The noise points don't participate in any cluster. Then start with the cluster label 1. Okay, you say that because initially we don't have any clusters, so we'll start with label number 1 and then apply this label to certain points. Okay, and how do we do that? For all the core points, go over the loop of over all the core points. If a core point has no cluster label, then give this label number 1, whatever is the current running label, give it to that core point. No, update it. So this is initialization. If there's no cluster label, you update this label by 1 and give it to this core point. Then label the current core point with this cluster label. Then, in addition to labeling that core point, you label all the points within the epsilon neighborhood of the core point, right, except the point itself, to the same cluster label. If the point does not have a cluster label, then label the points. So take all the points with epsilon radius. If that point does not have its cluster label right now, then give it your current running cluster label. Okay, so and just go through this loop. If you do this loop, you will slowly label all the points after some n clusters. The number of clusters is not predetermined, right? Because the algorithm will give you some number of clusters. But what is given to the algorithm is min points and the epsilon value. Now the question is, how do you find this epsilon radius and the min points? And there's always a problem in all the clustering algorithms. So we need to determine something. We need to give something to the algorithm to start with. Okay, so there is an interesting way of looking at it, because the problem is, like I was saying in the last class, moment you calculate density based on some radius or some size of that box, right? If this box size is not right for the data set, then you will get artifactual answers. You can get junk answers. So therefore, how do you determine the box size? How do you determine what is the epsilon radius and what is the min point? Both are actually connected. So therefore, to answer that question, there is one nice prescription for that, which is take a number k. Okay, so you have to start with something. You cannot get something out of nothing. So you start with k, and now consider the k nearest neighbor distance. So for various points. So what is the k nearest neighbor distance? So if I have a point here, and this is the nearest neighbor, this is my first nearest neighbor, this is my second nearest neighbor, this is my third nearest neighbor, this is my fourth nearest neighbor. So this distance is my fourth nearest neighbor distance for me. Okay, so similarly for other points there will be some other fourth nearest neighbor distance. So given a k, I can determine kth nearest neighbor distance. And so the point is, within a cluster, we assume that the points have roughly the same density. And the kth nearest neighbor distance determines some kind of a density, because we assume that all the points in a given cluster have roughly about the same kth nearest neighbor distance. And if you look at noise points, and noise points are obviously more scattered, they're more far off from each other, or the nearest even core points. Their kth nearest neighbor distance will be much higher than the kth nearest neighbor distance of points in a cluster. So what they suggest doing is, you take all the points in your data set. For each point, calculate the kth nearest neighbor distance. In this example shown in the figure, they are looking at fourth nearest neighbor distance. Okay, so you plot that. So for every point, you can have one distance. So if you have, like, imagine some kind of a DI, which is the fourth nearest neighbor distance for the ith point. Now plot these distances in a sorted order. Okay, so starting from smallest to in ascending order. So what will happen is typically you will see a flat region, or a region where the growth is very slow, and beyond a point you will see a sharp rise. So let us call this point some kind of inflection point, or a kind of a knee point, KNE point. Now, can somebody tell me what is happening within this stretch where the line is flat, the graph is flat, and beyond this stretch where there is a rapid increase? What do you think is happening here? Anybody?
It's not part of the core anymore.
Which is not part of the core? Which ones? So there are two sections here. One is the flat section, other is this rapidly rising section. Which is not part of the core?
The rising section is not part.
Perfect, very good. So basically, the fourth nearest neighbor distance. So all these points are pretty close to each other, because their fourth nearest neighbor distances are all nearby, right, or small. Whereas this sharply rising region is representing the points which are more scattered, more farther apart from each other. So therefore, these points represent the clusters, and these points represent noise, right? So this is where you draw a line. You roughly determine the ways of determining this knee. Okay, this is where you draw a line and say that whatever be that distance, right? Let us say something like this 10. So this 10 could be my. So what is this? What will this 10 be for in the Dbscan algorithm?
EPS.
Excellent. So that is your epsilon EPS value. So you and that is the EPS. Then what is the min points now?
2750.
No, no. Yeah, that's a bit misleading. Min points is because what is happening? How did you get this EPS? This 10. This is the fourth nearest neighbor distance of a point which is close to the border, right? Because all these distances that you are seeing in this graph are fourth nearest neighbor distances of points in the data set. So for all these points here, I hope you can see my cursor, the fourth nearest neighbor distance is 5. And when you go to the border of this section, the points are more scattered. The fourth nearest neighbor distance is 10, and so on and so forth. So if you are taking this point, so which means in that region, within a radius of about 10, there are only about 4 points, right? So therefore, so you have taken k. Okay, k is taken. That k will end up being the min points, and this threshold distance which you take from the knee point, that will end up being the EPS or epsilon. So that is, so therefore one problem with this is you have to choose k, but there is no other way. The same thing is summarized here. So distance from a point to its k nearest neighbor, that is called k dist or k distance. So for points that belong to some clusters, the value of k distance will be small if k is not larger than cluster size. For points that are not in the cluster, such as noise, the k distance will be relatively large. So compute k distance for all the points, plot them in a sorted order, and get the value at the knee point. Okay, and that distance becomes your EPS, and the k that you have taken becomes k is the min points, and the threshold distance becomes EPS. Right? If so there's still a problem, that is your choice of k is quite crucial. If k is too large, small clusters are likely to be labeled as noise, right? And if k is too small, even small number of closely spaced but that are noise or outliers have been incorrectly labeled as clusters. So this is a problem. Okay, so just see this animation. Let me go back. So I have a bunch of data like this, right? So how do you cluster them? We have taken one point, min points is 3. So here there are 3 min points from this point, so which includes this point. So therefore, this is a core point. And so you label this also as, so this is also a core point. This is also a core point. Also a core point. Almost a core point, this one also. This is a noise point. All right, and then you go to this one, this is a core point. Core, 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 core. Okay, so once you do that, you can see that all these are core, all these are core. And if you apply that rule where start with the first core point and then give cluster number 1 to this, then look at all the points within its epsilon neighborhood, give the same cluster to all these points. So give cluster 1 to these points also. Then go to this point. Okay, so it already has a cluster number. So then give that cluster number to its neighbors and so on and so forth, right? So like that, you'll give cluster number 1 to all these points one by one. Then you go to a noise point, you straight away remove. Then you go to the next core point, core point which is not given a cluster number. So give it cluster number 2, right? Because it's a right, and then give the same cluster to its neighbors and go to the next one. It's already labeled, so give its label to its neighbors, and so on and so forth. So the same label is propagated to all the points in the second cluster. So you label them all as cluster number 2. So at the end of it, you have 2 clusters, right? And noise point is removed. So note that in this whole approach, we are never talking about any kind of centroid. There is no representative of the cluster. The only thing is, if a given point has a certain cluster label, if another point is within the same certain radius from the first point, the new point also receives the same cluster label. So that is how the cluster spreads from point to point. And therefore, in this kind of a labeling of clusters, there is no need for the cluster to have a globular shape or a compact shape. Right? Because this can spread simply by neighborhood criteria. It can, extract odd shaped clusters and so on. So look at this example. So where I have, these are my clusters, so very odd shaped clusters. So I have 1, 2, 3, 4, 5, 6 clusters and lots of noise around that. And if you apply epsilon of 10 and min points of 4, right, the core points, border points, and noise points that you got are here like this. So note that at this point, we still haven't labeled the clusters. We have just labeled the points as core, border, and noise, right? And then apply Dbscan algorithm, right? So you get these clusters. So it is able to extract the clusters quite beautifully, right? And also the noise is all removed. Noise is all nicely identified. So it's quite resistant to noise, can handle clusters of different shapes and sizes. But even this algorithm, which is quite powerful when it comes to clusters of different shapes, right, has problem with data which has multiple densities, because even in this graph where we try to find epsilon and all that by looking at, so here also we're assuming that all the data where there are clusters has the same density, right? Otherwise, so if there are multiple densities, then the graph won't look like this. It might look, something like that, right? Each of them is a cluster of different density, but we haven't seen that case. We have only assumed a much simpler situation. Okay, so Dbscan works well in this kind of situations, but in cases where there are there's a lot of variation in density, Dbscan also will have a problem. So look at this kind of simple schematic where there are multiple regions. There are clusters A, B, C, and D, and there is this background N1 and N2. So the grayscale value, right, for each region indicates the local density. So A and B are high density regions. The background of A and B, which is N1, is slightly of lesser density. Then so then there is background of the other two clusters N2, which is of even lesser density. Then N2 has two clusters in it, C and D, which are slightly higher density than N2, but these are about the same density as N1. Okay, so you see that it's deliberately chosen to make the problem quite difficult. So in this case, what happens is if the epsilon threshold is low enough to find clusters C and D, then A, B, and N1 will be treated as a single cluster. Whereas if epsilon threshold is high enough to find A and B as separate clusters, then points in N1, C, D, and N2 will be marked as noise. So let me illustrate this using a simple, by showing it differently. So imagine that okay, so let us say I will draw the local density. So this is like A, this is like B, this is like N1, the background N1, and this is C, this is D, the background N2. So now you see that, so what is a cluster depends on my threshold for density, right? If I draw the threshold, apply the threshold here, then A and B will show up as clusters, separate clusters. And N1, N2, C and D will all be just marked as noise. Whereas if I lower my threshold and like this, then C and D will show up as sorry, this whole A, B, N1 will all become one big cluster. Then C and D will also become another cluster. Okay, so thing is, so ideally what you want is to identify that A, B, C, and D are four clusters. That is not going to happen with Dbscan because of your choice of threshold. If choice is if A's threshold is high, then A, B are picked up. If threshold is low, C, D are picked up, but then it will merge A, B, and N1 all into one big cluster. Okay, so this schematic clearly illustrates the problem with Dbscan. Right, and also it doesn't work very well with varying densities. This is what we mentioned before, and also with high dimensional data. So, for example, in this case, there are the same problem. Here you have a schematic. The same idea is shown here in a realization of a data distribution which has lots of variation density. Right, if you apply Dbscan to this, if you take min points for an epsilon, right, 9.92. These are the clusters that you got. And same thing if you reduce epsilon a little bit, that means increase the density threshold a little bit, right? You got these three clusters, but we've missed this and this. This low density clusters are completely ignored. Just like what we saw happen here. Okay. Same thing is happening here. So that's Dbscan algorithm. It's a very important algorithm, quite powerful. It is free from a lot of problems that we saw that were there with K-means clustering. Now, it has the problem of this variable densities in clusters. Now, for that, so basically what we need is a criteria for density, which is context dependent, right? You cannot have a fixed density as a threshold for the entire data set. You need to vary your density threshold based on the context. So, for example, in this N1 context, ideally I should have higher threshold, this whole region. In the N2 context, I need to have a lower threshold. But so how do you know what is the correct threshold in a given region? So this becomes a even more tricky problem. So we look at a different approach to clustering called graph-based clustering. Okay, so and where we are able to define this kind of a we need to define some kind of relative density. We need a concept of relative density. So with that, we'll be able to solve problems like this. And that relative density can be, to define that, we'll have to use graph-based clustering algorithm. So that is, how do you represent the points as nodes of a graph, right? If points are nodes of a graph, what are the edges of a graph? Right? How do you define that? And within that graph, then how do you define clusters? Right? Then how do you define relative densities in those clusters? So we'll see all of that in the next class. Yeah, so I think I'll break here, and I'll continue this in the next class. Any questions?
So just to confirm, Dbscan is not iterative. Like you just do it once. You classify everything once and it's done.
No, iterative in the sense you start. So first you label all the points as core, border, and noise. After that, you actually label the clusters, and that is iterative in the sense. So what happens is, in case of k-means, your clusters are represented by the centroids. And centroids are computed iteratively. Here, there's nothing like centroids. You just go ahead and put these cluster labels on the core on all the points which are not noise points. That is done point by point. So in that sense, it is iterative.
Right, but you're going over all the points only once.
Only once, yes.
Okay.
Yeah. One pass, you're done.
Okay.
Any other questions?
Sir,
Yeah. Go
so in
ahead.
the graph, what did the x-axis mean, that number of points?
Where? In that
Uh,
graph, that yeah, 1 second. This one, right?
Yes, sir.
Yeah. So x-axis is just the. So let us say the data set has 3,000 points. This is so you are plotting this like a, I don't know. You just x-axis is the point number. So data set has 3,000 points, right? Let us say I have just 10 points. 1, 2, 3, 10. And for each point, there is a k nearest neighbor distance that I compute. So I'll call this D1. For 2, it is this. For 3, it is this. 4. So I'm plotting it like a, I don't know what you call this. This is like a bar chart.
Understood now, sir.
That's all. Okay. It's not a continuous variable. It's just a point number in the data set.
Okay, sir. Got it. Thank you, sir.
Okay. Any other questions? This is nice. I want to get some, because Dbscan is a bit subtle. K-means is very easy to understand. Dbscan is a bit subtle. That's why I want to go slow. Spend some time discussing this. I think we'll have a demo of this on Friday. Sandeep?
Yes, sir. Yes.
Dbscan will have a demo. So thing is, if we can walk through the algorithm and see how it labels the points one by one.
Okay.
That will give a real grasp of the algorithm. So
Okay.
theoretically, it sounds simple, but you may not be comfortable unless you actually see it working on a small data set.
Right.
Any other questions?